In the field of tissue engineering, cells are often taken from their natural environments and placed into man-made cell culture systems where scientists attempt to study the natural cell behavior and control it. But standard cell culture is usually very different from the natural cell microenvironment, which can actually change cell behavior. This presents a huge challenge for tissue engineering. How can we study and control natural cell behavior when the tools we use to do that end up changing it? Well, my colleagues here at the University of Michigan at Professor Lahann's lab are trying to solve that problem. Hi, I'm Clark Teeple, and today I'll be discussing the research I'm involved in at the Lahann lab. I've been working with my graduate student mentor, Stacy Ramcharan, since September of last year, and I was able to continue my research over the summer thanks to the SURE program. My research is focused on creating synthetic scaffold structures that will accurately replicate the natural cell microenvironment. These scaffolds could be used for tissue engineering applications like tissue regeneration and drug delivery, where the scaffold would act as a new and improved means of cell culture. So traditionally, you might think of doing cell culture on plastic petri dishes, but this is not a good substitute for the natural cell environment. Petri dishes only allow cells to grow in 2 dimensions, which can put unnatural stress on the cells and cause changes in morphology and behavior. An alternative to petri dishes are hydrogels, which suspend the cells in a 3D matrix of naturally derived material. This is much better than a 2D system, but hydrogels still don't mimic the chemical and spatial complexity of the natural cell microenvironment. Also, they're often very poorly defined in terms of chemical makeup. A final alternative to both of these cell culture systems is to generate porous 3D scaffolds out of microfibers or nanofibers. These fibers can have internal chemistry as well as surface chemistry to interact with cells in a specified way. This approach allows cells to grow in 3 dimensions, has very tunable chemistry and mechanical properties, and is chemically well defined. All of these features make it our method of choice. When I joined the lab in September of 2013, a scaffold fabrication process had already been designed and developed by my colleagues. It generates fibers from a polymer solution and uses an automated control unit to create organized structures that function as tissue engineering scaffolds. My project began with the challenge of introducing the ability to control the composition within a scaffold by adding a fluidic device to the existing manufacturing process. This will promote new innovation in the design of our scaffolds and allow us to tailor our scaffold design to each specific biomedical application. To tackle this problem, I helped design and test several prototype devices. After characterizing the fibers generated by the devices using confocal fluorescence microscopy, we determined the limitations of each and we chose the best one to move forward with. Our next step was to interface our fluidic device with our existing fabrication process. After some preliminary tests, we decided that since our process was already controlled through the computer, the best way to implement our fluidic device would be to automate it through LabVIEW software. I attended a training session on LabVIEW programming and used that information to write several programs that linked our new fluidic device to the existing process. With our newly interfaced system, our plan is to begin testing how our automated fluidic device performs under actual scaffold generation conditions. And then we want to continue to improve the versatility of our manufacturing process. So now I'd like to take time to thank Professor Joerg Lahann for being a great sponsor, Stacy Ramcharan and Jake Jordal for being wonderful mentors through the year, and all of the other awesome members of the Lahann Lab for their support. And thank you for watching.